Subscribe to this YouTube channel by clicking the subscription button below. For future webinars and online short courses, please visit our website at australianwaterschool.com.au. Welcome everybody to this 60th Australian Water School webinar brought to you by iSwarm. This webinar series brings you the brilliant, innovative thinking coming out of the global water sector. And it's a great greeting to everybody. Welcome for joining us. My name is Trevor Pillar. I'm the National Partnerships Manager here at iSwarm, and I'll be the webinar chair. But look at that map just there. Thanks for joining us so early and being part of this webinar today. You can see there's people from across the globe here with us. So take part, discuss, and let's get right into this. What's happening over the next few weeks? Look at that on the screen there. We'll look at this first. There's a ton of things. I won't go into each one, but I want to highlight the one in yellow highlighted there because through April, on Tuesdays through April 4th, 11th and 18th, we're running Unconventional Gas Series, which this webinar covers a fair bit of what we're going to do then, but in nowhere near the detail. So you can see that Joel's just put on the screen there the website where you can register for these three courses. We're doing the webinar today, as you can see there, 27th of Feb, but online course 1, online course 2 and 3 are running through April. Yep, they're just being highlighted. Thanks, Joel. So we'd highly recommend that if you're interested in this topic, Ben, Karine and other presenters will be bringing that series of courses to you. But for today, I'm really delighted to introduce Ben and Karine. Thank you both so much for joining us today and for the effort that you've gone to in putting this together. Ben is a director at Aris Water, completing his PhD at Central Queensland University. 20 years experience, research, built and operated a wide range of water treatment facilities. He's a leader in the management, treatment and beneficial use of wastewater streams that have difficult chemistry. He's developed, patented and successfully commercialised 2 treatment technologies. Karine had 10 years experience in soil science, soil and water contamination from agriculture and past industrial activities. Strong in the area of soil microbial activities. I've just highlighted in blue. She's worked at CSIRO in Australia and in the French research institutes, and has a lot of background in farm productivity and carbon sequestration. So wonderful to have you both. Ben up there in Queensland, in Australia, Rockhampton in Queensland. Hi to you.
Hello.
And you're doing well. I can see that your office is packed to the gills behind you.
Always doing well when I'm to you, Trevor.
That's a great asset to hear that. And Karine, you're in Adelaide.
I am. Good afternoon, Trevor.
Enjoying the continuous dry weather. We haven't had rain for probably weeks. Who knows how long?
That's right.
We'll see rain eventually when
hopefully
it comes down from Queensland, where Ben is hogging it.
Yeah, it's just started to rain out there now, Trevor.
Make us feel envious and jealous all at once, Ben.
The weather is immune to criticism.
Look, we'll get straight into this, I reckon. Karine, you're going to take us off from the start, and then you'll hand over to Ben. Right over to you, Karine.
Thanks, Trevor. Thanks, and good afternoon, all webinar attendees. Just want to make sure you can see my screen right now.
Looks good. Yep.
Good, excellent. So we can keep going. I'm going to give you a pretty brief and general overview of unconventional gas exploitation in this next 15 minutes or so. We'll start with a few definitions about what unconventional gas is and some statistics about production and the proportion of unconventional into the global natural gas resources. And where these resources are is also important, and what the debate about unconventional gas is as well is important. So pretty big topic. It will be again a very quick overview, but because more details will be given in the online course in April, as Trevor said. So first, to start with, what is unconventional gas? As you probably all know, oil and gas are formed where organic matter has been deposited within the sediment and buried and compressed and heated for very, very long times. So transformation increases the pressure within the rock, and gas or oil will move upwards to other rock formations where it will form reservoirs that can be tapped into and mined. It's not always happening this way though, and in all rock formation, when the permeability is lower, some gas can be trapped within the rock, whether these rocks are sandstones or limestones or shales. This low permeability of the rock will make that the movement upwards will be impeded and the gas will tend to stay trapped in the rock. So in the case of sandstones and limestones, we tend to talk about tight gas, and shale gas is contained in shales. Now, shales are formations characterized by a finer grain structure, the clays, which are the smallest grains in the soil, and they have low permeability, and with the more limited ability of gas to flow through the rock, then it means that the volume of recoverable hydrocarbon gas in that case will be about an order of magnitude less than conventional resources per surface area. So the shale gas production will be more complex and costly than if it is in a conventional reservoirs. Now, there is also gas which is trapped in coal bed, in coal seams. So coal bed methane and coal seam gas are the same thing. And along with tight gas and shale gas, they form unconventional gas. Now, unconventional gas are part of a broader category of fuels, which are fossil fuels, which are also made of oil, tight oil and shale oil, and also other components such as methane hydrates or oil shale or oil sand. Now, oil shale and shale oil, it's a bit confusing, but it is not to be confused because oil shale is a sedimentary rock, a shale with a solid organic matter content which hasn't been transformed into oil or gas yet, but it can be heated and mined to produce oil. Now, if we look at the natural gas production, these are data that I got from the International Energy Agency, In 2017, natural gas production has hit a record 3,700 billion cubic meter, which is about 3.6% increase compared to 2016. And it's certainly the largest increase since 2010. You can see here that little steeper increase. If we look at the OECD countries, which are the green producers here at the bottom, Australia has more than tripled its production since 2004. This is the light purple little snake. It becomes the world's 8th largest natural gas producer in 2017. The first one is the US, followed by Canada and Norway. And Norway's production has reached an all-time high. If we now look at the IEA, there's EIA and IEA, so this one is the International Energy Agency. It estimates that there is about 208 technically recoverable resource, 208 trillion cubic meters, of technically recoverable resource of shale gas. And just for information, the conventional gas is about 421. Russia, Eastern Europe, and the Middle East are the biggest producer of conventional gas, as can be seen from this graph here with the light blue bar, which is a conventional gas in Russia. And the Middle East, Iran, Saudi Arabia, and Qatar. On the other hand, there are countries where the biggest resource is unconventional gas, such as China, by a big distance really, and Argentina, Mexico, Australia as well, that you can see here, whereas the US, for instance, it's about 50-50. So in terms of the top 10 countries with technically recoverable resources, Australia comes about the 7th. China is the 1st. That doesn't mean that the resource is being produced, but it's there. If we look at the world shale oil and shale gas basin, this map is the direct illustration almost of the figures I've given you before. It comes from a report that covers the most prospective shale formations in a group of 41 countries that had sufficient amount of geological data for resource assessment. So the red colored areas represent the basins for which estimates of resource were provided, whereas the beige areas here represent basins for which an estimate wasn't given because of lack of data, and the white countries were not assessed. Let's now have a look at the international situation, because the presence of resource doesn't mean that it doesn't necessarily go together with exploitation and commercial production. The list of countries that I've chosen to talk about now is not exhaustive, but it gives an idea of the different realities of the shale gas exploitation depending on the country. Of course, the first one we need to talk about is the US, because it is the birthplace of unconventional gas. The Barnett Shale in Texas was the first large play to be exploited at large scale, with intensive drilling starting in the late 1990s, I think. US now is one of a handful of countries where there is commercial production. And this boom, which the shale gas revolution, which happened in the last decade, sees that now there's 60% of US domestic gas production which comes from unconventional gas. It was made possible due to a combination of factors. First, geological features, experience with hydraulic fracturing, which started in the 1940s. Infrastructure also, pipelines and rigs are there, and there's big networks present. Companies that are ready to invest. Land ownership status is a big one because it incentivizes landowners to allow operators to drill on their land, contrarily to the Europe situation or Australia as well. US landowners usually own the minerals underneath their land. It's called the law of capture. So as I just said, Australia, Europe, different. Now, in terms of regulation, shale gas is regulated at all levels, the federal, state, local levels, and it's being produced in about 16 states. EU, fairly different situation. The resources were discovered from about 2010. Even though the reserves are deemed significant, it means that granting of concessions or prospection or exploration licenses have been done already on a number of countries. But there's no production yet, commercial production, as of 2015. I think the UK has resumed some fracking end of 2018 with Quadrilla. Regulation, the EU legislation is not fully equipped to tackle environmental impact. It doesn't mean the countries individually are not, but European legislation is different. And this lack of clear legal framework environment is probably not also conducive to investments. So not much commercial production happening in the EU. China has seen some significant progress for shale gas in 2017, and the production is expected to double by 2020. The problem is that the population density is a lot higher than everywhere else. The water scarcity is also a problem. So fracking is made harder, hydraulic fracturing, I should say, or fracking, is made harder despite government's high target to produce more. Let's have a look at Australia. So commercial production, because this is where we are, obviously, commercial production of coal bed methane began in the mid-1990s in Eastern Australia and has grown sizably over the last few years. Pretty much all outputs come from the Surat and Bowen Basin in Queensland, and small volumes also come from the Sydney Basin. The rapid growth of unconventional gas industry is supported by a strong demand in the Eastern Australian market, and it also reflects the Queensland government energy and climate policy, which require that electricity be produced from gas for 13% in 2005 up to 18% in 2020. I should say that on this map there is a pretty big basin here, the Beetaloo Basin in the Northern Territory and the Georgina Basin, which are not represented, but they're there. Now, if we can talk a bit about the debate or the consensus for this slide, I should say, which is that the goal is about replacing fossil fuel energy with renewable energy, of course, but a diverse energy mix, including fossil fuels, will remain probably in force in the foreseeable future. Natural gas now has some advantages. It has a lower carbon footprint compared to other fossil fuels, and it represents, therefore, an important bridge to a future with more renewable energy and less carbon. On the downside, a key constraint is that unconventional gas doesn't have, in most places, the degree of societal acceptance that it is required in order to boom and flourish. And without concerns being addressed, it may be impossible to convince the public that the risks are acceptably small and that it can be sourced without any problem. The issue of hydraulic fracturing is at the center of the debate, of course. It's important to remember, though, that not all coal seam do require fracturing. A report from the University of Technology in Sydney estimated in 2011, I think, that 10% of wells required stimulation, so it's very different to the US situation. I thought that this coal seam gas was best illustrated by the Roman god Janus, who has a double head looking in two different directions, the one of the aspirations and the potentially enormous benefits, and the one of the anxieties related to the environmental sustainability, the sustainable use of water, both of which, the aspirations and the issues, that have to be treated with equal weight and seriousness, of course. Let's have a look at the Australian situation, which is a good illustration also of opposite paths taken by different states. This map represents the fracking bans in the different states and territories. So it goes from fracking, which is completely authorized in Queensland, no restriction about exploration and development, to complete ban in Victoria or Tasmania with a moratorium that is in place until 2025. All the other states, WA, New South Wales, South Australia, NT, have some part of the land or the territory which can be allowed for fracking, some from which it is banned. So South Australia, it's allowed on 98% of the territory, and 2%, I think it's the limestone coast, which is a karstic environment. It's banned there, as far as I know, and WA banned in 98% of the territory. The Northern Territory, the moratorium has been lifted in April 2018, so now it's banned on only about 50% of the state. So what are the environmental impacts? Very briefly, fracking involves the injection of pressurized fluids to stimulate the shale or coal seam and release the natural gas. So the fluid contains sand, which is pumped in with water, 99% of water, and chemicals also. Most experts would consider that the key environmental impact and risks associated with shale gas project or coal seam gas project are about the use of water and the potential pollution of water through groundwater abstraction, about the use, or potential contamination, wastewater disposal, or discharges. Air emission is also important, with emission of VOC, volatile organic compounds, or methane. And community impact also is a big one. Land use, we were talking about farmers at the beginning of the talk, and biodiversity, noise, traffic also have to be taken into account. So if we look at this diagram that I presented before, here are the impacts for the compartments that I talked about: surface water, habitat, air quality, groundwater. Noise is missing from it's not a compartment, it's an impact. But these are exactly the different topics that have to be regulated and addressed when looking at an approval. I highlighted the surface and the groundwater because this is exactly what Ben is talking about, not so much the surface and groundwater, but what to do with the water produced. And there will be more on the approval process, particularly on the 4th of April. Thank you, and speak to you soon.
Thank you, Corinne. We'll change over. So it's a pleasure talking to you all. Hope you're enjoying it. There hasn't been too many questions yet, so feel free to ask questions. So unconventional gas, why are we looking at exploiting this resource when renewables are all the big thing? I suppose we've got to keep in mind that all forms of energy production that we do has an environmental impact. The Greens Party here in Australia was actually formed campaigning against a renewable energy project, which was a hydroelectric dam in Tasmania. So no matter what way we get energy, we do actually have an environmental impact from it. Unconventional gas is a fossil fuel, but it does emit less greenhouse gas than burning coal or oil. The best way to look at it is as a transitional energy source. If I can get this to go, there we go. So if we have a look at some of the peer-reviewed science coming out about transitional energy, you can actually see that coal is very much on the way down as percentage, and gas is actually increasing quite substantially. But you can get really depressed if you think about it, because the population of the planet is increasing. The amount of people who are moving out of extreme poverty, which is a good thing, is also increasing, but that means that there's tens of millions, if not hundreds of millions more people who've got access to energy. So you can actually see that even though the percentage of coal as far as the amount of energy which is being used is decreasing, the amount of coal is actually increasing, the amount of gas is increasing, oil as an energy source is increasing. And when you have a look at where they're talking about in the peer-reviewed scientific articles on transitional energy, they're not talking about us swapping over to renewables within 10 years to meet a 2020 target or 2030. They're talking about 50 years, 75 years, as far as being able to move over to the majority of the people on the planet using renewable energy. So things such as unconventional gas as a transitional energy source, they've actually got decades worth of transitional period to prove. So it's really important to have a look at these types of things. So what's unconventional gas's relationship with water? Shale gas is actually a net consumer of water, so it uses more water than what you get water back out of the well. Coal seam gas is a net producer of water, so you'll use some water during the drilling, but it's basically the coal seam is so wet that you'll actually more water coming out of that well than what you use to drill it. Both of these types of water have environmental issues. One of the main ones is salinity, and in amongst that, it's different types of salts, but you've got the sodicity coming through there being a major issue. Then you've got some elements coming through, arsenic, lead, strontium, those types of things. So yeah, they're there in a big way as well. And the cost of treatment is higher than the value of the water. Otherwise, every farmer would have used this water during the drought. So be able to get that water at a huge expense to be able to get the water so that it's actually being treated. So we get all these different pictures coming through about what the underground looks like and what we're seeing, but it does tend to look an awful lot like this, that you've got multiple confined aquifers, layers and seals of oil, gas, briny water. It doesn't look particularly neat. So you see an awful lot of diagrams where everything's nice, neat, straight lines. It's not. Things get mixed up and you get different types of water quality. So having a look at the shale, which you want to be able to do with shale water, is not just use it once. So when you're basically transporting the water in to be able to use it to drill a well, you are looking to be able to recover some of that water and then reuse it again and reuse it again. And part of what the water treatment in the shale water cycle is looking to achieve is, you know, years ago, that water used to be able to use twice, maybe 3 times, being recycled and drilling wells. Now they're up to 5, 6, 7 times. So it's more being able to treat water that you're recovering from the well during the drilling process, so that you have to bring less clean water to site. So major area for shale gas water in Australia is over in Western Australia. It's got well-educated stakeholders. So using the International Olympic Swimming Pool standard here, 3 Olympic swimming pools for a vertical well. You've got about 8.5 Olympic swimming pools for a horizontal well. And in comparison, 10 hectares of a vegetable crop would typically use 60 Olympic swimming pools. So yeah, each well's not using too much water as you go through. If you consider that a gas field may have 30 wells, 40 wells, up to 100 wells, you can start in quantities of water. CSG Water, every gas company would prefer that it's not there. Some wells have got a large amount of water, some wells have got small. The industry is now old enough that we can have predictions versus actual water volume comparisons. So back in 2005, when the Queensland industry was quite new, the Queensland government and academics thought that a mature industry would be producing between 120 gigalitres a year and 300 gigalitres a year. The actual volume in 2018 was 60 gigalitres a year, and now the maximum water production from a mature gas industry is expected to be between 70 and 80 gigalitres a year. And this is much less than the government predictions. It's only about 25%. It's less than even what the industry thought was going to happen. And one of the reasons why that's thought is that multiple wells in the same aquifer, there's a cumulative depressurization effect. And that's why they think that those original models were so far out. But this is a good thing as far as the industry is concerned, because there's less water that needs to be managed. One of the reasons why this is so complicated is that this is basically a spreadsheet that identifies how the produced water volumes are calculated. And all I want you to get from this is that it's a multiple variations that will have an impact on how much water is being produced. This is the traditional graph, which is brought up just about by everybody about how much water is going to come out of the well. You can see that the water volume decreases as the well ages and the amount of gas coming out of the well increases. Part of me actually hates this graph because what it doesn't show you is that wells quite often will have workover crews come through which aim to refurbish the well, basically get out any contaminants which may be blocking gas from getting out of the well. So as a workover crew comes through, that water will spike up and down as it goes in. So yeah, it's a good generic diagram, but doesn't quite mimic what a well really does. So this is having a look at the differences between some modelled productions and real water productions. And I suppose it gets back to the old saying that all models are wrong, but some are useful. And the more ground truthing that we can do on our models, you can see that that one was reasonably close, but that one was really out as far as how much water was going to come out. And as the industry is maturing, there's new drilling techniques which are having a big impact on this as well, such as when the industry started and the coal seam gas, they were all vertical wells. Now you've got horizontal wells which are being drilled. They're much more water comes out when those wells are initially commissioned, but they drop off very quickly as far as produced water volumes are concerned. And you can see that a bit here. We're on the far right-hand side of the graph. In the latest modelling technique, where the you can see that the number of wells has increased, but the amount of water which is actually being produced is tapering off. It's not increasing at the same level. And part of that is that depressurization effect, the cumulative effect that we were talking about there before, but drilling impact also, the method of drilling also has an impact on that. And what does this mean? You can see here in the world that the North America, so that's Canada and the United States, are having a big increase in the amount of water which is coming through. Over here in Asia, that's mainly Australia along the eastern seaboard, which is responsible for that kick up there. Europe is expanding quite slowly, and so is Latin America. So designing a water treatment plant, what does this mean? Key design criteria, you look at your volumes of water that you've got coming in, so your minimum, your maximum, your average. You have a look at your inflow chemistry, so what ranges of contaminants of concern are you going to have, such as salinity or strontium or fluoride, the level of treatment which is required, and that very much focuses in on how's that water going to be reused. And reuse in the unconventional gas industry is quite varied. So you can have in-house reuse, where the treated water is used to drill wells or to make concrete, to basically in the manufacture of wells. You can have treated water used for dust suppression on roads. Then you get into agriculture, where treated water can be used to water stock or to irrigate crops. And then you can have indirect environmental discharge, where treated water is put into river basins. All of these different beneficial use arrangements of the treated water have different guidelines and different requirements as to how that water needs to be treated. And you've also got to keep in the back of your mind that there is no such magic places away. So if you're taking things out of that water, such as coal fines or brine, as far as salinity is concerned, that also needs to go somewhere, and that needs to be managed. And that can be quite difficult, particularly in the eastern seaboard of Australia. If you think that the majority around the world, the most common form of getting rid of brine is sea disposal, but we're 300 to 400 kilometres away from the sea. So that brine needs to be reused or managed, where the most common form of disposal is not available. So having a look at CSG water, why is it difficult to treat? It's highly variable. If you can have a look here, this is some inflow water and some treated water from a real CSG treatment plant. You can see that it's got coal fines in it. That's from a new well. As a well comes online for the first time in its commissioning, you get lots of coal fines in that water, and that decreases over time. That water is quite saline. We're talking 4,000 to 5,000 milligrams per litre TDS, or 6,500 to 8,000 electrical conductivity units. Yeah, that needs to be treated and removed, but it will also vary over time. As the wells dewater, it's not unusual for certain contaminants of concern, such as salinity, fluoride, strontium, boron, bromide, to actually increase in concentration. Sometimes for things such as fluoride, up to 10 times concentration from when the well was first drilled to when it's well and truly into its dewatering stage. So that makes it quite difficult to design a treatment plant. If you think about a sewage treatment plant in Sydney or Melbourne or Adelaide, you just don't get that type of variation in wastewater treatment. But with this type of industrial water treatment, you've got a large amount of variation. So you need to build a treatment chain which has got a multiple barrier approach and quite able to handle changes over time. Salinity is a big concern, particularly sodium salts, because sodium salts will impact on clay soils, and clay soils are very common around the world, very common in agricultural areas. And if you start irrigating clay soils with a water with a high sodium absorption ratio, those soils will suffer environmental impacts. Heavy metals, if we're talking about coal bed methane and shale gas over in the United States, you talk a lot about arsenic. Arsenic isn't so much present here in the Australian scenario. It's in very low concentrations, but things like strontium are actually very common through the Bowen and Surat Basin. So you've basically got to assess your inflow chemistry, your inflow volumes, and then determine how that water is going to be treated and how it's going to be reused, and design up a treatment chain for that to work. You can't cut and paste treatment chains in the unconventional gas industry from gas field to gas field. Something that will work in one area may not work and suffer considerable issues if you put the same treatment chain somewhere else. And that's because of these variations. So I realize this is quite a busy slide for an online webinar. All I want you to get from this is the range of things, such as if we head to bromide 1.3 to 12.7 or 2.8 to 11.5, these are quite significant ranges in concentration. Iron is very bad in reverse osmosis treatment technologies. So 0.16 isn't going to cause you a problem, but 45 milligrams per litre, that'll clog up your membranes in an RO plant incredibly quickly if you haven't got the right pre-treatment involved in your treatment chain. So yeah, highly variable and not easy to design a treatment chain around. And this is just a graphical looking at how the groundwater chemistry changes at different well sites across a gas field. And you can see that sodium is one of the major contaminants of concern. So is chloride, calcium and magnesium, which are an important part of the sodium absorption ratio, are hardly there at all, which makes that water very difficult to irrigate. This is a graph, a picture, sorry, having a look at the most common forms of treatment technologies in the unconventional gas industry. And you can see that things which are up here just at the lab scale, emerging, moving on to established, extensively used and saturated. So one example of saturated is ultrafiltration, and the other one is media filtration as far as moving solids out, such as those coal fines that we were looking at there before. Risk management. Believe it or not, this is a published risk management which has got a huge amount of red in it. I'm not sure how many of you are involved with risk management on a day-to-day basis, but normally with a recycled water scheme, you would not see anywhere near this amount of red. So it's important to acknowledge that the reuse of unconventional gas water does carry significant risks with it. They need to be managed correctly through a risk management approach and to get your treatment chain right, and not just with your recycled water, but being able to dispose of any contaminants of concern that you've got there as well. So one of the big things which occurred in the Australian industry is the water storage. Images like what we had here with large-scale evaporation ponds caused a great deal of concern with stakeholders, environmental groups, government regulators, that this is quite an expensive way of managing CSG water, because all of those ponds need to be rehabilitated at the end of the gas field's life. And if you consider that each pond or dam, a rule of thumb, depending on the size and the soil type, is that it's at least $1 million per dam to be able to rehabilitate that back, you're looking at a fair amount of money just over here. What the industry is more moving on to is tanks, portable tanks that can be put up in a relatively short period of time with a lined base, so you're not actually contaminating the soil. So when that gas field is being decommissioned, the sludge is pumped out of the tanks, taken to a regulated waste facility. The tanks themselves are deconstructed and basically moved on to the next gas site, and there's no soil contamination underneath those tanks that need to be rehabilitated, unlike what's occurred with these dams. So it's a much more cost-effective way of being able to manage water storage in the unconventional gas industry. Brine, as we were talking about there is no such magic place as a way. There's been lots of ways discussed on managing brine in the unconventional gas industry. A lot of people have tried to sell the salt or done studies as far as selling the salt, but it's never been able to be shown to be economically viable in the unconventional gas industry, because it's not just sodium salt that you've got there. you've got strontium salts, arsenic salts, all sorts of different heavy metal salts there in relatively small concentrations, but it's not going to actually meet the standard as far as human consumption. So when we look at brine management strategies around the world, you've got disposal, minimisation, indirect use, and direct use. In the unconventional gas industry, we have tended to focus on disposal and minimisation. So deep well injection, aquifer recharge with brine is one thing. Ocean discharge is quite hard to do in the Australian environment, but it is used internationally in quite a few places. Indirect use, evaporation ponds, crystallising, going down to a zero liquid discharge. All of these things are tried. They are in use in various locations, but once you start going down to here, it's quite expensive. If you've got a waste heat source, it's quite will reduce the cost, but you've still got to put that salt somewhere. So old mine sites, registered landfills, those types of places have been used, but they've got their own costs with them as well. So if we actually have a look at how brine's managed around the world, sewer discharge and surface water discharge are the most common, and if you consider that most sewers head out to sea eventually, even if it's a inland sewer heading into a river, just between those two there, you're getting almost 3/4 of the brine around the world is discharged into an ocean eventually. You've got evaporation ponds, land application, deep well injection, but because these are much less common forms of managing the brine and the salinity, that means that they're much more expensive. So that covers me pretty much for today, I think. And we've got a lot more detail in the lectures coming up as far as different technologies that can be used, different reuse purposes, specific water qualities that need to be maintained. So, yeah.
Fantastic. Fantastic, Ben. Look, that's and Kareen, we've had a feast here today. It's been absolutely brilliant. I appreciate the effort going in here, and we can see such a huge range of issues that you've raised just in this 30 or 40 minutes. We've got about 15 minutes left. One thing that really stood out as I was talking to CEO here on your screen right now, you see if you hit that Q&A button, definitely put in your comments and questions. We'd love to have them. But one thing I was talking about with Darryl Day, the CEO here, was that there's a real need for a three-way level of confidence between the community, the industry, and the regulator. I just wondered whether you had any comments around that. I know that I haven't talked about science there, but if those three were had a level of confidence between each other, then there'd be a lot more likelihood of a way forward as we progress the energy issues facing each country.
Yeah, I'll just answer some of these questions which have come up here if you like. So Katie, yours which has just come in, what do I mean by saturated? It's basically that every single water treatment plant in the industry is using that type of technology. So where we're talking about media filtration, those quite often mean sand filters or ion exchange media filters, and they're very commonly used as a cheap, robust and reliable method of removing things such as coal fines. Hydrocyclones would be another one which is there. So by saturated, I mean that everybody's using them. So Tina, with the how do we go to considering CSG water as a resource? I'm in an interesting position where I'm actively researching with the CSG industry, but we actually have water treatment plants out there in the real world treating CSG water every day. And with all of the ones that we've got up and running, and the majority of people who are out there, it's 100% recycling. That we've got farmers who are actually using the water and being able to, a large part of the eastern seaboard of Australia has been in drought over the last 18 months, 2 years. We've actually had more problems with farmers being jealous that they're not getting the treated CSG water and being able to keep irrigated pasture or keep watering their stock in a time of drought. Yeah, neighbours who don't have access to the water tend to put in more complaints. That the farmers that we've got beneficial use agreements with are absolutely loving it. And so
That's certainly not the message that you hear generally spoken and written about across the industry.
Yeah, well, it's an interesting thing that the lock the gate movement, or the number of signs that you see, and the lock the gate movement have got very, the concerns that they're raising are not illegitimate concerns. They are quite serious concerns. But if you've got your water treatment right, and if you're managing the waste, such as that brine stream that we were talking about there before, in a sustainable manner, there are very few farmers out there who are not going to knock back what is essentially free water in the time of a drought.
Well, I wrote this note before we started that often these gas extractions happen in, not always, but quite often in arid areas, and you would think that the farmer and the miner would be close friends.
It also very much depends on where your CSG application is located. If you consider the CSG industry in a large part of Queensland, in the Bowen Basin, the northern part of the Surat, it's located adjacent to open cut coal mines or underground coal mines, and they're much larger farms. So you're talking about a 10,000 hectare farm or a 5,000 hectare farm. So you're dealing with 3 or 4 stakeholders. What happened in New South Wales was that a lot of the CSG industry tried to start up much closer to the coast. Farms were much smaller. You had much higher numbers of stakeholders. And the management of stakeholders and how that water was, how they were approached. Yeah, gas engineers are sometimes not the best people to actually go out and engage with people who are concerned about the sustainability of what's going to happen on their small farm. Yep. So yeah, it's been good for that.
That one there by Aptu, can you see that question up top there? One from Malang in Indonesia. Thank you for the best presentation. What's the best method for water contamination treatment, especially in Australia?
Reverse osmosis is used an awful lot, and that's mainly to do with the salinity concern which is coming through. But you've got to get your pre-treatment right. If your pre-treatment's not right, as far as being able to remove things such as iron, strontium, bromide, things that will clog your membranes. So then you start looking at ion exchange media as far as being able to remove that. You need, no one technology will work on its own. You've got to develop up a treatment chain of complementary technologies that will actually work through there as well. With the sustainability issue, as far as the free groundwater, the groundwater which is being taken by the CSG industry, any aquifer which is pretty much in a coal seam is not suitable for farm irrigation or farm use without extensive treatment. So no farmer would be getting a license to actually go down into these coal seams and extract the water and be able to use it on their farm to water stock or irrigate crops. And that's because as part of the geochemistry of it being located in the coal seam, it picks up a lot of other things as well, such as the sodium salts that we were talking about, the fluoride, the strontium. And most of these CSG bores, they're in a confined aquifer in Australia between 300 metres and 1,000 metres down, so call it a kilometre down. Most farm irrigation bores are up at the 50 metre mark, 100 metre mark, much closer in a freshwater zone. So yeah, they're 2 different levels of water. So no farmer is basically putting down a well where they've got to extract water and then put the water through a water treatment plant. So the water treatment plants in the CSG industry, each one will treat, depending on the size of the gas field, between say a megalitre a day up to 5 megalitres a day. And they will cost somewhere between $3 million and $10 million to install, and around $1 million to $1.5 million to actually keep running, operational costs per year.
Yep.
And this is not something that a farmer is going to be able to do. Now, where that water is treated by the gas industry and made available to the farmers, it's basically sold off for $1 a year or $1 a megalitre. Yeah.
Thanks a lot, Ben. There's a long question coming in on the chat line from Stephen Aponsa. The topic of the webinar suggests the application of sustainable development framework, triple bottom line, balancing social, economic and financial to the gas industry, the management of the gas industry. But the emerging report by the Royal Commission indicates sustainable development framework is not appropriate for the management of natural resources. My question is, why do you still advocate the use of sustainable development framework despite the emergent debate over the use of triple line? I'm not sure we can deal with that entire question in the only remaining few minutes we've got left, about 2 or 3 minutes actually.
I'm aware of the Murray-Darling report as far as the Royal Commission with the South Australian, which has only just come out. It was either at the end of last month or the beginning of this one. The reason why we frame it this way is a lot of the legislation is framed that way.
Yeah.
So we've got guidelines and regulations which are all off sustainable management and risk-based management approaches.
Yeah.
So I'm aware of those recommendations from the Murray-Darling report, but to be honest with you, it is going to be years before the Australian regulations and guidelines change, even if those are all adopted. So,
Well, we're up to 57 minutes and it's gone like it's really gone fast. There's just so much material to deal with. It's been really great. Thank you, Karine. Thank you, Ben. As some of the attendees have just said, the best presentation they've seen. Thank you both for the presentations. I couldn't agree more. I really appreciate you taking the time over this. Can I just wrap this up now? And you can see the free webinars coming up there. Coming down to the online courses, you can see the 4th, 11th and 18th. Thanks, Joel. That's just been highlighted. They're the courses that I think you'll go into the much more detail than you could ever do in a 1 hour webinar. But they're all online courses. We encourage you to join us for that. Some face-to-face courses there, and of course subscribe to our YouTube channel and also to Twitter. That would be fantastic. Any closing comments, Karine or Ben?
If you want to leave the questions and answers up for a while, Trevor,
then we can maybe going on that.
Yeah, that's fantastic. And should anybody want to ask some more questions afterwards, by all means, shoot them to us. We'll get them across to Ben and Karine and keep the conversation going. That'll be fantastic. But for now, I think we might leave it at that. And it's been terrific. I hardly believe an hour's gone by. It's been so interesting. Thanks, Karine. Thank you, Ben.
Thank you.
And I look forward to the courses coming up and hope to see you soon. Bye for now.
Bye.
Bye.
Subscribe to this YouTube channel by clicking the subscription button. For future webinars and online short courses, please visit our website at australianwaterschool.com.au.